Welcome, everyone. Today, we'll explore a powerful technique that moves beyond the limitations of standard regression outputs, contrast analysis. Standard regression coefficients, while useful, often restrict our comparisons to a single, arbitrary reference group. However, economic questions are rarely that simple. We often need to detect trends, compare specific steps between groups, or decompose complex interactions. Contrast analysis provides that essential analytic lens, allowing us to perform precise, custom comparisons that directly answer these specific economic questions. For example, instead of just knowing general wage effects, we can determine specific insights, such as manufacturing wages being significantly higher than service wages, independent of base levels. This approach acts as a crucial bridge, connecting our statistical estimations with deeper, more substantive interpretations of our data. So, let's delve into how contrast analysis helps solve the problem of limited comparisons. The first critical step in any robust analysis is to precisely define your research question. This will directly dictate the most appropriate statistical tool to employ for your comparisons. Our navigation map here provides a straightforward guide, linking 5 common types of research questions to their corresponding Stata commands. For simpler inquiries, such as determining if a single group differs significantly from a base category, standard regression coefficients or the lincom command are sufficient. However, as questions become more nuanced, requiring comparisons between specific groups, testing for trends across ordered categories, or evaluating all possible pairwise differences, we turn to more specialized commands like contrast or PW compare. For outcomes on a probability scale, margins combined with contrast offers the right approach. Crucially, while different commands can fit your model, the contrast command excels at automating complex hypothesis testing efficiently and accurately. Understanding this workflow is vital for drawing precise, meaningful conclusions from your data. Contrast operators are powerful prefixes that allow us to specify the exact type of comparison we want to make within our models. Think of them as a versatile toolkit for precisely decomposing the effects of a categorical factor variable. The R operator, for reference, is the default, comparing each level of a variable to a predefined base category. When we use A, for adjacent, we are looking at step effects by comparing each level I to the very next level, I plus 1. The G operator compares each level to the grand mean, or the overall average of the variable. For ordered categorical variables, the P operator allows us to test for polynomial trends, such as linear, quadratic, or cubic relationships. Finally, the H, or Helmert operator, compares each level to the mean of all subsequent levels. These operators are fundamental to leveraging the contrast command, which we'll explore next, helping us to decompose factor variable effects into 1 degree of freedom comparisons. A critical distinction in comparison testing is between balanced and observed designs. This choice fundamentally affects how group means are weighted in our analysis. The as-balanced approach, which is the default for the contrast command, treats each group as if it contained an equal number of observations. This is ideal for experimental data or when you are interested in theoretical population means. In contrast, the as-observed approach, used by PW compare and margins, weights the means by their actual sample frequencies. This method is common in observational data or predictive modeling, reflecting the real-world sample composition. Choosing between these two orientations is crucial because it can significantly impact your estimates and p-values, especially in unbalanced datasets where group sizes vary greatly. For example, comparing wages for 2 industries, one with 1,000 workers and another with 50, a balanced contrast gives equal weight, while an observed comparison would heavily weight the larger industry. This choice is vital to consider for statistically sound analysis. At its core, a contrast is a linear combination of model parameters, such as regression coefficients. The key defining feature is that the coefficients in this linear combination must sum to 0, which ensures we are testing a specific difference or comparison. The hypothesis for a contrast is formally expressed as L beta equals 0, where L is our matrix of contrast coefficients and beta is the vector of parameters. The statistical test used to evaluate this hypothesis is the Wald test. The Wald statistic, W, essentially measures how far our estimated contrast is from the null hypothesis value, scaled by its variance-covariance matrix. It incorporates the matrix of contrast coefficients, the estimated parameters, and the variance-covariance matrix. For nonlinear models like logit or probit, where direct calculation is complex, Stata employs the delta method to approximate the variance of these nonlinear functions, such as probabilities, allowing for the construction of these Wald tests. Now that we have a sense of the math, let's look at a crucial piece of syntax required to perform these analyses in practice. For our contrast analysis to be valid, several assumptions must be met. First is normality. The model's residuals should be normally distributed, which is particularly critical for small samples. Second is homoscedasticity, the assumption of equal variance of residuals across all groups. If you suspect this is violated, it's highly recommended to use robust standard errors with the VCE robust option. Third is estimability. If a specific combination of factors doesn't exist in your data, an empty cell, the contrast cannot be estimated. Stata provides the empty cells reweighted option to handle this. Finally, proper model specification is key. As we've discussed, interaction terms must be explicitly declared using the double hash syntax for contrast to decompose them correctly. If you're studying the interaction of region and occupation, but your dataset has no surgeons in the northeast region, that's an empty cell. A contrast involving that specific group would fail unless you address the estimability issue. Assuming our model is well specified and meets these conditions, let's see how to interpret the output with a practical example. Once you've run your contrast analysis, the next crucial step is translating that statistical output into a meaningful economic narrative. This slide serves as a quick guide to interpreting the results from our key contrast types. First, with a reference contrast, we're comparing a specific category to a designated base. If your coefficient is positive and significant, as in our example, you can state that wages in sector A are higher than in the base sector. Next, the adjacent contrast helps us understand stepwise changes. A positive result here means moving from a bachelor's to a master's degree increases wages by a specific amount, quantifying the effect of moving up one level. Finally, polynomial contrasts reveal trends. A significant linear term suggests a steady trend, while a significant quadratic term indicates a curve or flattening effect, like experience having a positive trend that flattens over time. The crucial takeaway here is don't just look at the p-values. To truly understand the economic implications, always examine the sign and magnitude of the coefficient. This allows you to articulate not just if there's a difference, but how much and in what direction that difference lies, providing rich, actionable insights. To finalize our understanding, let's compare contrast with other important Stata post-estimation commands. This helps us choose the right tool for different types of hypothesis testing and interpretation. The test command is for simple, manual custom hypotheses, giving you just an F statistic and p-value. Contrast, our focus today, shines in automated decompositions, testing joint hypotheses, trends, and interactions, often providing richer output like ANOVA tables and effect sizes. It's particularly useful for as-balanced designs. For nonlinear models, margins allows you to obtain predicted values on the probability scale, aiding interpretation, and it defaults to as-observed weighting. Lastly, PW-compare is designed for exploratory analysis, performing all pairwise tests. Be sure to use multiple comparison adjustments with PW-compare to avoid type 1 errors, a best practice we discussed earlier. The command you choose critically depends on the precision and scope of your research question. Before we can use the contrast command, we must tell Stata how to treat our variables. This is done using factor variable notation. The I prefix tells Stata that a variable, like education, is categorical. This is a mandatory prerequisite for using contrast. The C prefix indicates a continuous variable. The double hash creates a full factorial model, which includes the main effects of each variable plus all their interaction terms. This is essential for decomposing interactions correctly. Crucially, you cannot use contrast with manually created dummy variables, for example, using gen_male equals gender equals 1. You must use the I notation. In the command regress wage I education #C experience, Stata understands that education is a categorical factor and experience is a continuous variable. It will automatically create the necessary dummy variables for education, a term for experience, and the interaction terms between them. With the correct syntax in place, we can now explore the different types of comparisons contrast allows us to make using special operators. The basic syntax for the contrast command is straightforward. Contrast, followed by a term list and optional settings. The term list is where you specify the variable and the operator for the comparison you wish to make. For example, r.race compares each race category to the base category, utilizing the reference operator we discussed earlier. To compare adjacent age groups, you would use a.ageGroup, which tests for stepwise differences. You can also test for interaction effects. Race checks sex tests the overall interaction effect, whether the effect of race on the outcome is different for different sexes. To get more specific and decompose an interaction, race at sex tests the effect of race within each level of sex. This allows for a very granular analysis of how effects vary across subgroups. The options part of the syntax provides even more control over the output and statistical tests, which we will explore next. Beyond the basic syntax, the contrast command offers powerful options for customizing both the reporting and the statistical adjustments of your tests. Under reporting control, the overall option provides a joint hypothesis test for all specified terms, giving you an aggregated view of significance. The effects option is particularly useful, as it ensures the output table displays the individual differences and contrasts you've specified, rather than just an F-test of overall significance, showing you the precise comparisons. Moving to statistical adjustments, mCompare method is crucial when performing multiple comparisons. For instance, Bonferroni is a more conservative method, ideal for a few pre-planned comparisons. Tukey is better suited when you want to compare all possible pairs of groups, often used with the pwCompare command. These adjustments help control the family-wise error rate and prevent false positives. Finally, the as observed option directly relates to the balanced versus observed designs. By default, contrast assumes a balanced design, treating all groups as if they had equal sample sizes. Using as observed switches this to weighting by the actual sample frequencies, which is more appropriate for observational data where group sizes are often unequal. This choice can significantly impact your results, especially in unbalanced datasets. Let's put these concepts into practice with a practical illustration of wage analysis. We'll utilize the well-known NLSW88 dataset, which contains information on young working women, to analyze the union wage premium. Our research question is twofold. First, do union members earn more than non-union members? And second, does this wage premium vary across different industries? To address this, we'll need to test for both main effects, which capture the overall union impact, and interaction effects, which reveal how the union effect might change depending on the industry. The Stata code block on the right outlines our initial steps, loading the NLSW88 dataset, performing a describe and summarize of our key variables, wage, union status, and industry, and most importantly, using codebook industry to confirm that our industry variable is correctly specified as a factor variable. This correct specification is a crucial prerequisite for conducting robust contrast analysis. Now, with our data prepared, let's start by analyzing a different variable, occupation, to see if there's a trend in wages as we move up the occupational hierarchy. Here, we investigate the relationship between wages and occupation level, specifically looking for systematic trends. We begin by fitting a simple regression model of wage on occupation, ensuring occupation is treated as a factor variable using I.occupation. Then, we apply the contrast command with the p operator to test for polynomial trends, examining both linear and quadratic relationships. The results reveal a highly significant linear term with a p-value of 0.000. This strongly indicates that, on average, wages tend to rise as individuals move up the occupational hierarchy. Additionally, we observe a significant quadratic term with a p-value of 0.043. This suggests that while wages generally increase, the relationship is not perfectly linear. The rate of increase might flatten out or curve at higher occupation levels, implying diminishing returns. This approach allows us to uncover nuanced patterns that a simple linear model alone might miss. Now we return to our main question about the union wage premium across industries. This requires an interaction model. We first fit a full factorial model using regress wage I union ## I industry. To test the union effect within each industry, we use the command contrast R union at industry. The at symbol is key here. It asks Stata to perform the comparison specified on its left for each level of the variable on its right. The output table shows the contrast, the wage difference between union and non-union workers, separately for the transport and sales industries. We see a significant union wage premium of 2.4 in the transport sector, with a p-value of 0.03. However, in the sales sector, the premium is only 0.8 and is not statistically significant. This result provides a much more nuanced story than a simple average union effect. It tells us that union membership provides a significant wage boost for transport workers in this sample, but not for sales workers. While this targeted approach is powerful, sometimes we don't have a specific hypothesis and want to explore all possible comparisons. For that, we use pairwise tests.
Building on our discussion of targeted hypothesis tests, sometimes our analysis is more exploratory. When we lack a specific, predefined hypothesis, we might want to compare every single group against every other group within our dataset. This is where pairwise comparisons become incredibly useful. To perform these all-pairs comparisons in Stata, we use the pwcompare command, as shown in the blue box. A crucial aspect here is the mcompare SIDAC option. This adjustment is absolutely vital. When you run many tests simultaneously, the probability of finding a statistically significant difference purely by chance, a type 1 error or false positive, increases dramatically. The SIDAC adjustment, like other multiple comparison corrections, controls this family-wise error rate, ensuring our findings are robust. Looking at the example output, we see comparisons between different industries. For instance, the difference between transport and sales is significant, as is the difference between professional and sales. However, the difference between manufacturing and transport is not statistically significant. The contrast column provides the estimated difference between the group means, while p greater than t indicates its statistical significance, adjusted by SIDAC. This allows us to confidently identify which specific industry pairs show meaningful differences, preventing us from making spurious conclusions from an exploratory analysis.
After conducting our statistical tests, the next crucial step is to visualize these results. While numerical tables provide precision, a graphical representation, especially for complex interactions, offers much clearer intuition. The margins command calculates the predicted outcomes for each group, which we then use with margins plot to automatically generate a profile plot. The most important aspect of interpreting this plot is to look for non-parallel lines. If the lines representing our groups, in this case, union and non-union workers, are not parallel, it provides compelling visual evidence of an interaction effect. It means the impact of one factor, like union status, changes across the levels of another, such as industry. Here, we can clearly see a substantial difference in predicted wages for union versus non-union workers within the transport industry. This gap significantly diminishes across other sectors, visually confirming our earlier statistical findings that the union wage premium is not constant across all industries. To summarize our discussion on contrast analysis, there are 4 key best practices to ensure rigorous and insightful results. First,
always use factor variables. The I notation is mandatory, as the contrast command depends entirely on correctly identifying categorical variables. Second, actively check for empty cells in your data, where certain subgroups may not exist. If encountered, use the Empty Cells Reweight option to ensure your contrasts are estimable. Third, it is crucial to adjust for multiple comparisons, especially when testing many pairs, to avoid p-hacking and false positives. The mCompare option can help manage this risk. Finally, always visualize your results. A complex interaction test is best understood when accompanied by a margins plot, which makes the findings clear and intuitive for both you and your audience.
We've covered a lot of ground today on contrast analysis, and for those interested in diving deeper, here are some invaluable resources. First, the official Stata documentation. The Stata Base Reference Manual provides comprehensive details on the contrast command itself, specifically for linear hypothesis testing. Building on that, the Stata Post-Estimation Manual focuses on using margins and contrast for post-estimation comparisons, which we touched upon with margins plot. For a fantastic online resource, I highly recommend UCLA IDRE Stats. Their guide on everything you always wanted to know about contrasts is incredibly practical and user-friendly. And finally, a great book by Mitchell, MN, Interpreting and Visualizing Regression Models Using Stata, offers a broader perspective on effectively presenting your regression results. Remember, as the quote aptly puts it, precision in comparison leads to precision in economic insight.